A mysterious title. I like titles like this in math. At the start of the lesson, you're like, I don't know why I even put the title up there. The title should be at the end of the lesson. Related rates at the end. What are we talking about here? It's quite possible that this will be the most powerful thing I show you all year. It's possible. This is amazing stuff. It's amazing all of a sudden the kind of problems you'll be able to do. I teach that grade 11 class in the afternoon, and I feel sympathy for them because they do math and they do math and they do math. And it doesn't seem like they can do anything when it's over. When grade 11 math is over, it's like, okay, but can we actually solve any real life type problems here? This, related rates, is like the top of the heap as far as, okay, now we can do something with all of this. I'll read this and then I want to talk about Leibniz. I'm going to get distracted by Leibniz again for a while. In related rates problems, we are usually asked to determine a rate when given information about a corresponding rate. So we've got the rate of one thing, we want to find the rate of a different thing. In most cases, these rates are measured with respect to time. Time really is what we're headed for. We've used x along the independent axis a lot. But when you actually go out there, that's usually time. You know what I mean? It's usually we're talking about time. So we're going to be talking about kilometers per hour, centimeters cubed per second, or something like that. Always time in the denominator. And I'm really going to get on about units today. And so on our mathematical form board, you might have been like, he didn't put units up there. I'm like, yeah, I was biding my time until I could prove that units is the whole story. Units is the deal in all this. So a lot about units today. Therefore, when differentiating, we'll be usually do so with respect to time. You're like, why? I don't know if you've proved that, but when I get distracted by Leibniz for a second here, I'll show you what I mean. These problems often require the use of chain rule and implicit differentiation that can be solved according to the following procedure. Usually. Word problems don't nicely fall into a recipe like this usually, but this is generally what we're going to talk about in related rates. Determine an equation that relates the quantity to be found with the given quantity. Well, we've been doing that for years. You get a question that's involving two things, you're going to try and find an equation that relates the two things. Differentiate both sides of the equation with respect to time. Almost always in these ones, we're going to do time, but we'll see. Substitute the known values and solve for the required value. Isn't that step 3 of every word problem? And then sub in and get the answer. Okay. But before I get into it, I want to talk about Leibniz for a second. And I'm just going to write a Leibniz derivative here, and I want to talk about what it means. And I'm going to sort of do an old one and a new one at the same time. I'm going to write down dy by dt. It's sort of like dy by dx, but this time it's with respect to t, because there's going to be a lot of t today. So this is the one I've chosen to talk about. And my question is, what does this mean? It means slope of tangent. Yes, it does mean that for sure. It means derivative. Yes, it definitely means that for sure. It means time. Oh, I don't want to, I wrote that there. I want to put that right there. Time is the dependent variable. And yesterday I didn't say dependent very often. What I said was the variable you're going to see in the question. That's what you're going to see when you get over there. Or the one you're supposed to be looking for in the question. You should be looking for t's. It means more, and I'm really jumping ahead here. I'm like jumping ahead a chapter and a half in my understanding of this here, but it helps today. This means that's delta y over delta t. That's what we were doing the whole time. We were doing slope. If this is slope, then dy by dt also means change in y over change in time. You're like, that's not what you said yesterday. You said this was a derivative. I'm like, I know. It's all of those things. It's the slope of the tangent. It's the derivative. And so this little dy at the top means delta y, a little tiny delta y. See, all that stuff that people get upset about was like, why did we even do that h stuff? Why did we do the 2 to 2.1, 2 to 2.01 stuff if we were just going to learn how to do quick derivatives? And the answer is to understand what this symbol meant. This means a little tiny change in y and a little tiny change in t. We've zoomed right in on the derivative and said, just this much. Just look at a little tiny piece. And those two things are just two little tiny pieces if we need them to be. Change in y over change in t. That's what that thing really means. That's the best explanation of all of them. It's how much y is changing with respect to t. So this explains why if the question, okay, this is the best thing I'm going to say so far. If the question has something like this in it, kilometers per hour, that means take the derivative with respect to time. Time's in the denominator. It's the delta t in the denominator. Centimeters cubed per second. As soon as you see that per second down there, you're like, oh, derivative with respect to t. I need dt on the bottom. I need delta t as the important variable. Okay? And I'm going to keep hammering away on that idea that as soon as you see a unit that's got time in the denominator, you're thinking time in the denominator. Delta t on the bottom, dt on the bottom, derivative with respect to t. That's a huge idea. And it could be that just clicks, because I've tried to set it up for a week or so here. It could be like, oh yeah, that makes sense. I get it. Or it could be that's going to take a little more time during the lesson to make that clear. Let's jump right into a problem. The radius of a circular oil slick on a body of water is increasing at a rate of 2 meters per minute. So oil was spilt into the ocean, and somebody's measuring and seeing that this circle of oil is growing at a rate of 2 meters per minute. The question is, find the rate of change of area of the oil slick when its radius is 50 meters. There's two tips-offs to the why this is this type of question, and I'll underline them in red. The first thing is, right there, 2 meters per minute. That's not red. Per minute. This tells me that whatever I go to do, I'm doing d something by dt, because that's time in the bottom. It's like screaming at me. The unit is saying we're looking at rate of change with respect to time in this particular question. Then the next big thing that shouts out at me is area and radius. Those are the two quantities we're talking about. They've given me some information about radius. I want to know some information about area. Well, I guess I'll circle circular because it tells me the shape I'm talking about. So then it comes down to, do I know an equation that relates the area and the radius of a circle? Did it sound like he was saying the rhyme there? He was saying the rhyme. Oh, that makes me happy. I love when I run into my grade 9 students who are saying the rhyme. Fuzzy Wuzzy was a bear. Area is pi r squared. I like related rates so much that when I write down that formula that relates the two things, that's when I order my pizza. I'm like, oh, you can order the pizza, Mom. I'll be ready in just a minute. I'm in the home stretch already. Just having the formula here is enough to make me feel like I've got this question cornered. Well, even though it's a circle, it can't corner a circle. Okay, you know what? A equals pi r squared. Now, this told me what I'm going to do. I'm going to take the derivative with respect to time, and we know how to handle this situation now. You're like, yeah, but I don't see any t's at all in this thing. I'm like, I know, it's good. I'm going to take d by dt of this side, and please don't freak out through this whole question that I'm about to do here as you're looking at that going, I don't see how we're going to do this at all. It all falls together. Related rates are beautiful like that. It just falls together. I don't know what A is, but I'm taking d by dt of it. I can't do anything, so I just write dA dt. That may be where you got to with implicit differentiation. When I get to a variable that isn't the variable I'm taking with respect to, I just write dA dt. That's an unknown in the question. You're like, well, I don't know what dA dt is. That freaks you out because you're like, I haven't even started this question. I already don't know what that is. I'm like, that's what they want. That's find the rate of change of area. That's what I'm trying to find. Okay, dA dt. That's what I'm after. Good news. Now, derivative of pi r squared. This is not t. I still proceed and do derivatives. Derivative of pi r squared is 2 pi r, which is a whole nother class of discussion why 2 pi r just popped out of that thing. Because circles, as the area increases, how much is the area increasing by? The radius. It's adding on a radius each time. Okay. But because this wasn't a t, when I go in there and I actually have to do chain rule. It's really like pi times, and I'll put a little bracket on the r, it's really pi r squared. I did bring down the 2, reduce the power by 1, but now I go inside to find that derivative, to find the derivative of r with dr dt. Yeah, good. That's what I said yesterday. You got to do at least enough of this homework where you go, yeah, I get what you do there. I don't know what the derivative of r with respect to t is, so I write dr dt, which now this is completely freaking you out at this point. You're like, so I had a line that I understood, a equals pi r squared. I differentiated it with respect to t, and now I've got a line of symbols. And what good is it to me? We'll get to that in just a second. Luke has a question.
So we know what the radius is.
Oh yeah. Do you see that you're 50% home at that point? I'm going to let you finish, but just let me interrupt for a second. We know what 2 is. Yeah, we know what 2 is. And we're not panicked about it. We know what pi is. Yeah? And so, especially you physics type people, you're like, I just got to sub into all this stuff now. Let's hope that the information is there. We know what r is. They told me what radius to use. Did they? 50 meters. Yeah? dr dt. Big moment. If we know dr dt, we are home free. Not only have we ordered the pizza, I can start pouring the Pepsi now because it is over if I know what dr dt is. Let me read the question. The radius of a circular oil slick of a body of water is increasing at a rate of 2 meters per minute. This is dr dt. Let's do a better job on questions after this one, where as we read the question, we label those things as we go, of what they are. That's dr dt. It's the rate of change of radius with respect to time. It's meters per minute. It's delta r over delta t. Sub and go. Label my subs here, yeah? Sub in. R equals 50 meters. dr by dt equals 2 meters per minute. Notice I'm getting a little uptight about units here because I really want to show off something awesome about units. You know, I didn't just say sub in r equals 50. I said 50 meters. I didn't say sub in dr dt equals 2. I said 2 meters per minute.
So you're just able to sub it the term minute and not like another like 60 seconds or something or 1 minute?
Oh, yeah. Well, see, this one, it said minutes, so I'm going to go ahead and do minutes. You're right, though. You got to watch out if they ask for it in seconds or something like that. I might have to do some conversions, but let's not get sidetracked by that just yet. That's a small, dangerous issue, is getting the right units in there. But this solves that problem, too. 2 pi, okay, what was the radius? 50 meters. I'm writing the meters in there now. And I got a good reason for it, because I want to show off some things in this lesson. And then dr dt, which was 2 meters per minute. dA dt equals, let's see, this is the way we normally do this, right? We go 2 times pi times 50 times 2, and I think we come out to 200 pi. And you can get that as a decimal if you want. I'm not crazy about the decimals. I'd rather have 200 pi. Why would you not rather have that than 628 point blah, blah, blah? How many decimal points do I round off to? Whatever. You know, this 200 pi is a great number to pass along in the question and just keep it like that. But there's more. I can see what the units are going to be here. If I keep the units as I sub in, I can see what the units of the answer are. I know you chem people. I watched, and I think she does a lot of this in class too, where she's playing around with the units. Meters, that's meters squared, over minutes. Oh, there's so much going on here. There's an unbelievable amount of mathematics going on here. The first thing is, does this make sense? They asked the rate of change of area. Does it make sense that the rate of change of area would be meters squared per minute? Yeah, that's how many meters squared you're adding on to the oil spill per minute. Next, look at dA on the numerator. This is change of area, meters squared. This is change of time, minutes. You see, it's all starting to match up. And then you start seeing Leibniz in a whole new light, which is Leibniz just telling you what two things we're talking about. It's just telling you what the delta y and the delta x are. What are we talking about? We're talking about delta A and delta t. Therefore, the rate of change of area is 200 pi meters squared per minute. An acronym for which part?
Rate of change.
Oh, yeah. We could have gone the ROC.
Right.
When it was instantaneous rate of change, we went IROC. When it was average rate of change, I went AROC. Any questions about that? Let's go back to the procedure and see if I followed the procedure. The procedure said, determine an equation that relates to quantities. Yes, I went A equals pi r squared. Differentiate with respect to time. Yes, I did that. Sub in the required stuff. Good. So the only thing I'm going to refine on this is identifying what the stuff is before I start. That is, when I read a question, I'm going to identify what these things are as I go. Oh, I love this question. I'm going to say that every time. Every question that comes up, I'm going, oh, I like this one. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 meters from the liftoff point. Let me just add to my diagram right now. Oh, this thing's bugging me. Where am I going to put it? I got nowhere to put it. Maybe right there will be out of danger. So what we got here is, maybe orange is a good color for this. There's the rangefinder. The rangefinder, 500 feet from the liftoff point. So this whole distance here is 500 feet. Good. At the moment, the rangefinder's elevation is pi over 4. I'm going to use theta as my angle in the question. We like theta there. And the angle is increasing at a rate of 0.14 radians per minute. So what is this in terms of the symbols and Leibniz notation that we've been talking about? Let me simplify it.
0.14 R over M I N.
Right, yeah, that's radians per minute. So radians in the top, that's d theta. Minutes in the bottom, that's tt. That per minute tells us when the time comes, I'm differentiating with respect to t. It says, how fast is the balloon rising at that moment? What am I trying to find? I'm finding out how much the height is changing at that particular time. I'm looking for dH/dt. How much is the height with respect to time? Now maybe finally the title makes sense. Related rates. Apparently there's a relationship between d theta dt and dH/dt. Ooh, could there be? Could someone on the ground measuring how much the angle is changing figure out how high this balloon is moving through the air? Is it possible from the ground to be able to tell that? The answer is, of course it is. Look at all the things we can do from planet Earth. We can study all the planets and all that. Of course we got this all figured out. And here it is. Where's theta? There's theta. There's h. And what I need is an equation that relates theta, h, and 500. What equation relates these? Trevor.
Maybe sine law?
Sine law could be. Okay, so good. He's on the right track here. We got some trig going on here. Let me just help a little bit. They said this thing's going straight up. If you're like, What if it wasn't going straight up? Well, then we'd be sine law, cosine law. There'd be other choices to do if this wasn't going straight up. This is going straight up. Relative to my angle, this side's the opposite, and this is the adjacent. Now, what equation are we talking about? Tan. Tan. You're like, at first you're like, oh no, tan, not tan. And then you're like, well, wait a minute. We know tan. We can do derivative of tan. It'll be all right. Okay. So, tan theta equals h over 500. We good so far? Just some old trig. And I'm going to rearrange that just ever so slightly to get ready for the derivative. Tan theta equals 1 over 500h. I don't know if you need that, but it's a little bit better for finding derivatives when that's a coefficient as opposed to a denominator. That's how I get out of trouble of automatically making this a quotient rule, which it doesn't have to be a quotient rule because that's just a number. So make it a fraction out front. Question?
Why did you make the angle theta and not pi over 4?
Oh, yeah, good question. Good question. Let's get back to that in just a second, okay? Because the reason is, as this thing's rising, theta will take on all sorts of values. And at some point, I want to talk about the angle pi over 4. Yeah, at some point, I want to sub that in. Yeah, absolutely true. Not unlike the previous question. Why didn't I make r 50 at the start? Because the only information I would have got is what's the area at that particular moment. And I wanted more than that, so I said, okay, leave r out until I get the relationships I want, and then put it in. Yeah.
Theta is like our variable for the angle.
Right, so apparently theta is going to pop out. Well, theta's already in there, but apparently theta is going to pop out. And I'm not going to be upset when d theta dt pops up because I got that information too. That's not going to annoy me too much. My diagram got incredibly large here. Oh, I got some space down here. I'm going to be okay. Now, d by dt of both sides. And I'm writing this every time for teaching purposes, but it could be you're at the point where you're like, I don't have to write d by dt on both sides, but it really is showing off what you're doing. It's making derivative into an operation. I'm doing d by dt of both sides. So, derivative of tan theta. Now, this is derivative of tan theta, not with respect to theta, with respect to some other variable t. So at first, I'm like, okay, well, I can still do tan theta. Derivative of tan theta is
Secant squared.
good. It was on the memorized board, so hopefully we have that one memorized. Secant squared theta. We don't want to have to get sidetracked and figure out the derivative of tan in the meantime. But
Do we have to put that over dt? Or?
not yet. Yes, you're right about something. Tan theta, secant squared theta. Then go inside the tan, and I get d theta dt, which looks a little complicated, but we're not actually panicked about that. We're like, d theta dt? Oh no, now I got to know d theta dt. Because we made the effort earlier to label those things, we're not bothered by d theta dt appearing in this at all, okay? And then this side, derivative of 1 over 500h would be 1 over 500 times dh dt. And again, if you're not prepared for these questions, when these symbols all pop up, it looks like, what an absolute mess I have. But there's 3 things I got to know. I got to know theta, I got to know d theta dt, and I got to know what 1 over 500 is. Okay, I know what 1 over 500 is. That one I'm less worried about. Yes?
So you split up the h in the fraction, so you have h times 1 over 500. If you were to get the derivative,
If you did it as a product rule, is that what you mean? You'd be derivative of the first, which,
this looks like you still have that fraction there without taking its derivative, even though you have it in the brackets.
yeah, I'm with you. So what you're saying is, what about the derivative of 1 over 500? You know what I mean? Like, how's that in there? So if you took this out and did it as a product rule, you'd get derivative of the first, 0, times the second, 0, plus derivative of the second, dh dt, times the first, 1 over 500. Yeah? So when you make a mistake, it's not a mistake, and you do one of these questions with product or quotient because you just didn't see it coming, you'll get the same answer anyways. You just have a little 0 in there that takes care of things, yeah? So, you don't have to isolate here, actually, because you could just sub in. But I'm going to isolate just in case you run into a question that wants you to do those isolations. I'm trying to get in this question, how fast is the balloon rising? I want dH dt. So I'm just going to bring this 500 over here and make it into 5 secant squared theta d theta by dt. I'm sort of okay with that isolation over there, but other people aren't, that it's isolated this way around. So instead, I'm just going to reverse those two and just go the other way around and go, okay, dH dt equals 500 secant squared theta d theta dt. I've just exchanged those to go, well, if this is equal to that, then I can just write it the other way around without worrying about the negatives and everything like that. Now, sub in theta equals pi over 4. This is when I'm subbing that in now. This is the relationship the whole time. I want to know specifically at pi over 4, what's the relationship? And d theta by dt equal to
0.14 r over min.
rads per minute, yes? Ooh, I'm low on space here. dH dt equals 500 secant squared pi over 4 times 0.14. Just enough room down here. dH dt equals, let's see, secant squared pi over 4 is 1 over cos squared pi over 4. 1 over root 2 squared, 2, 1,000 times 0.14 is 140 meters per, what were we, minutes? Seconds?
We were
Minutes, meters per minute. You can type it in your calculator. You don't have to do it in your head like I did. I did it just to prove we can do those in our heads if we really, really wanted to. But okay, no, use your calculator. Yeah, for sure, use your calculator. Don't let me freak you out. Let's just sit back and savor this for a minute. Question. Oh, yeah, she's like, weren't you playing around with units here? And where I got the meters from was that 500 feet right there. I didn't do a great job of carrying it around. Here's feet right there, 500 feet. Then when I brought it over, 500 feet. So this is feet. Yeah, why did I put meters there? Good question. I see what you're saying. I thought you meant like, where did you find that in the units of the question? You didn't mean that. You mean it was feet, dummy. Yeah, absolutely. Yeah. Question.
When you make it like theta, are you still going to do like A for the first unit, or you put an A instead of theta? Like where you go A plus H minus H after H. You can like the next question would be like, it says how about 600 feet, right?
Yeah, we kept the theta in there because the theta could have been anything. This is now an equation by right there. I haven't been specific at all. This is the equation of the situation all the way through the flight. So yeah, theta is like the A in the question. It's like, okay, now you can put in whatever you want. And we leave it as a theta. You're right. If we had kept going with the A's, if we had kept the A's all the way along, then this would have been A, the specific value in the question. Put your specific theta in here that you want to study. Because apparently this changes. If this stays at a constant rate here, it means this won't stay at a constant rate. So there's a little more than meets the eye here to what the relationships are here and whether they make sense. Like even to go back to the previous one, I almost got sidetracked by saying, how much oil would you have to pump out to keep the radius growing at the same amount? You'd have to be pumping out more and more and more oil because it's getting bigger like this. Like just think about blowing up a balloon. To get that first couple of inches of a balloon only takes a couple of seconds. But once it's like this, adding on, it needs so much air to add on. And that's the same with a circular oil spill. Let's say it was 50 meters wide, this oil spill. How much oil would you have to add another meter on? Like it's unbelievable. So these relationships maybe aren't exactly realistic yet about how those relationships work together. And the same here. This would probably result in this thing not going at a constant height change, yeah? Okay. That's not really what you asked, but I want to show you the bigger picture anyways. Any questions there? Did I follow the recipe? Get a equation for the relationship between the two variables, differentiate with respect to t, and then sub in. They usually work like that. 3. Oh, here we go. Just the exact thing I was talking about. Air being blown into a balloon. How many of these do I have to do? There's 6 total?
Yeah.
And the last one, the second last one's really hard, and the last one's really easy. Okay. I remember now. Air is blown into a spherical balloon so that the volume increases at a rate of 200 centimeters cubed per second. Now that's more realistic. It's more realistic that the amount of air going in is constant, like the first one. It would be the amount of oil that's going in probably that's constant. You know, not how big the thing's getting, you know. 200 centimeters cubed per second. So what is that? Big moment in this lesson. If you can look at that and know what that is in Leibniz notation, oh, you are home free. Let me read it again. Air is blown into a spherical balloon so that the volume increases at a rate of 200 centimeters cubed per, it's right there, centimeters cubed per second. It's screaming at you at what it is. I put the arrow over there. Maybe it should be there.
So would the rate of change be 200 centimeters cubed over a second?
Yes, that's absolutely true. But in Leibniz notation,
So
what
d,
it,
d centimeters squared, no, d 200 centimeters cubed per second?
right, and so what is centimeters cubed? What are we talking about there? What quantity? Volume. And what's changing on the bottom?
Seconds.
That's dv dt. Now, finally, you're getting convinced on Leibniz. It's not v prime. V prime's like, derivative. This is like very specific. How much is the volume changing with respect to time? So they've given me dv dt. If compression of air is neglected, oh, what a wacky detail. As you blow up a balloon, the balloon starts fighting back more and more, and it compresses the air a little bit, and then the volume actually starts changing. So the volume of air you put in isn't the volume you get at the end, but we're just going to ignore all that for now, because it's really not a big deal. It's not a big deal to deal with that stuff later, but okay. How fast is the radius increasing? Okay, how fast is the radius increasing? What are they asking here? What are they looking for in the question if you want to know how fast the radius is increasing? In Leibniz notation, let's get to Leibniz. dr dt. We're looking for dr dt. So when dr dt pops out of the question, we're not going to be stressed. We're going to be like, yeah, good. I'm glad dr dt popped out of this. And then at the instant the diameter is 30 centimeters. Well, that's the same as it always was. And I really feel like it's going to be asked for radius by the time I'm done. But okay, that's other information to sub in. So the question is, can I come up with an equation that relates volume of a sphere to radius of a sphere? That's not an easy formula to remember. But does anyone remember it? Why is that happening? We'll talk about that later. Max?
4 over 3 pi r.
Why would you remember that? All right. Volume equals 4/3 pi r cubed. And for me, with related rates questions, that's pizza ordering time. Once I've got the right equation, the rest of this is pretty nice stuff. Derek? No, no fancy rhyme for volume equals 4/3 pi r cubed. I do like that this is true though. I'll show you in a minute. I'll actually do the derivative and I'll show you. It's like, there is a way to not remember it, but sort of like remind yourself that it's right. Okay, so by reading the question properly, I'm like d by dt. That's what I'm after here in this question. So I'm going to go d by dt of this side and d by dt of this side. So, you got a decision to make. You see v, and we're taking derivative with respect to t. I don't know what that is. And yeah, it's just dv dt. It's like, what is the derivative of v with respect to t? It's dv dt. It sort of demystifies it when you say it like that. Now this side, it's r's, not t's. So I've got to do chain rule. That is, I do the derivative of this thing normally, so I get 12 thirds pi r squared. Then go derivative of the inside, which is dr dt. Maybe you didn't need that step. Maybe you're like, 12 thirds, why did you write it like that? 4 pi r squared dr dt. And let's talk about 4 pi r squared for a second. What's 4 pi r squared in terms of spheres? That's a surface area. And now think about a sphere. Every time you increase the volume, you're adding on a layer of surface area around the outside, like a wrap of tinfoil around the outside. So it's not that surprising that surface area popped out of this thing. Okay, so what? I'm feeling pretty good because dr dt is what I wanted, right? So you don't have to isolate here. You could just start subbing in right now. But I'm going to do it just to show it off here. I'm going to go dr dt then would be dv dt over the 4 pi r squared. And I've exchanged the sides there just because dr dt is the one that I really wanted. And then sub in dv dt and r equals. You know, I'm arrogantly presuming at this point that these are the things they give me in the question. What was dv dt? 200 centimeters cubed per second. And radius was, oh, look at them trying to be tricky. Remember grade 9 math? This was the tricky question. Let's see, what am I going to do to really challenge them on the measurement test? Maybe I'll give them diameter instead of radius and see if they notice. Yeah?
So 15
15 centimeters. Hopefully that doesn't derail us during all this. You know though? Like if you get an answer here and all of a sudden you look and go, why is my answer double what theirs is? Maybe that clues you, you're like, maybe I'll check the radius diameter thing. Okay, so here we go. Dr dt equals dv dt, 200 centimeters cubed per second, divided by 4 pi times 15 centimeters squared. So let's just deal with the numbers first. I know I'm carrying those units around, and I want to talk about that, but what do we get? 200 over 60 pi, which I'll reduce to No, that's completely wrong. Hold on. I did something in my head that I shouldn't have done.
Would you not square the 15?
Yeah, sure you would. 200 over 225 times 4, 900 pi.
So 2 over 9 pi.
2 over 9 pi, which you might think is awkward, but I think it's actually less awkward than getting this as a crazy 0.0 something decimal. You know what I mean? Let's talk about the units for a second, because for just a moment it seems like it's not right. Centimeters cubed per second divided by centimeters squared would be centimeters per second. See, the units really help here to go, am I doing the right thing? Because it was dr dt. How much is the radius increasing with time? Notice that it's a very small amount. It's tough to, once you get balloons up to 30 centimeters, it's tough to add on. You need a lot of volume to add on. And if that's not perfectly clear, imagine the Earth. Say I'd blown up a balloon the size of the Earth. How much air would it take to grow this thing another centimeter? You need a whole layer of air around the outside of the Earth. A lot, so you get these really small numbers for dr dt. Any questions about numeral 3? A lot of related rates questions are like this. As long as you can come up with the formula, d by dt both sides, and plug them in and go. How am I doing on time? Oh, I'm doing great on time. More time here? Oh, I was lying. Remember last time I was like, oh, I love this question. It's my favorite. I love these ones. These are good. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner, is now moving straight east. What? I'll draw a picture in a second. When the cruiser is 1.2 kilometers north of the intersection and the car is 1.6 kilometers to the east, the police. This is the question that they make fun of. There's these type of questions in movies and shows, say. They're trying to make fun of math classes. And they're like, they start talking about a train is moving at this speed. What is, like it's impossible or something like that. It's not. It's great. Great question coming up. All right. The distance between the cars increasing at 40 kilometers an hour. If the cruiser is moving at 100, whatever. Okay, blah. I don't really read word problems like that. I don't get hung up in the details. I'm like, I need a picture of what's going on here. I can't even picture what's going on. I got a police cruiser to the north, and the car is to the east. Here comes my diagram of this situation. It's a highway with
There's your
the dotted line, yeah. Didn't really get those yellow dots down the middle, but you get the idea now, right? All right, so a police cruiser approaching a right-angled intersection from the north. So here's the police cruiser. Now you get to see if I'm any good at drawing things, and boy, you're going to find out I'm really not. Police cruiser coming up. Looks like a little spaceship. Is this right? Black front and back, and then white in the middle? Or is it the other way around? I don't remember. Police cruiser. Did I put it in the right spot? Approaching a right-angled intersection from the north. Here he comes. He's heading this way. That way. Good. That's not a bad picture for me, actually. Okay, stop. A car that has turned the corner and is now moving straight east. So here's you trying to get away from the cops. In your red sports car. Here we go. Sports car coming up. With red tires. No less. And you're heading this way, trying to get away. That's one of the best diagrams I've ever done, actually. That's how low my standards are. It's amazing.
Between each car as well to the corner.
Yeah, we know lots of stuff. There's lots of subbing to be done here. But what we need is a relationship between what I'll call y, the x,
Y would be at the bottom because the police car speed is the dependent variable. So X what?
Oh, I don't know. Per hour. Those are all DTs on the bottom.
Right.
So we're going to eventually find the
Time.
derivative with respect to time. Yeah, okay. So anyways, I'm going to add one more line in here that might help us find the relationship between these.
Is this 10 again? We know our opposite and our wait. We don't have an angle.
Here's the important line in the question. I'm going to reread it and focus on one line. Okay, so now I'm going to read it. After I get my diagram, now I'll read the question. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. Got it. When the cruiser is 1.2 kilometers north of the intersection, so at some point I'm going to use y equals 1.2 in this question. And the car is 1.6 kilometers to the east. That's x equals 1.6 that I'm going to sub in at some point. The police determine that the distance between the car is increasing at 40 kilometers per hour. So the police point their radar along the orange line there at the car and say this distance is changing at 40 kilometers an hour. So the d is involved here. So someone asked, is this tan again? And it might have been, except that we need a relationship between x, y, and d.
Pythagorean?
It's Pythagorean Theorem. That's what the relationship is. X squared plus y squared equals d squared. When you first see it, I can feel your brains freaking out like, oh no, how am I going to differentiate that? Oh, implicit differentiation sitting there going, it's not a problem. You can have as many variables as you want. I don't care. As long as you got the subs for it, it's no problem at all. In fact, the derivative of this is really nice. Let me do it very quickly. By dt, 2x dx dt plus 2y dy dt equals 2d dd dt. It's pretty nice. You go back to the day where we did tough derivatives. Derivative of top times the bottom minus derivative of bottom times top, now common factor, square roots, all this whole thing. This is nice. The question is, do I have the subs for it? That's what really comes out. What am I trying to solve in this question? What am I trying to get? Because there's only 1, 2, 3, 4, 5, 6 things here. I'm not as intimidated as I could be. Trevor, question.
When you were reading the question, you didn't mark down
Oh,
all of your...
no, I didn't finish marking them down. You're right. Because I got sidetracked by the relationship between the three of them, and then I went and did this. So now let me go back and relabel these things and see if I have everything we need. The distance between them is increasing at 40, so that's dd dt. That's how much the distance is changing between the two objects. The cruiser is moving at 120 kilometers an hour. That's dy dt. That's how much the y is changing. Is that enough information? I need x. Got it. Need y. Got it. Need dx dt. Oh no, that's what I'm trying to figure out. Dx dt. That's the question mark. So that's okay. I don't need that. Dy dt. Got it. dd dt. Got it. I feel pretty good about the whole situation. And I'm going to do this one the other way because I don't believe isolating is the right way to go here, because I'm just going to make a big mess. I know on the video I isolate here, but I think it's like, why are we isolating here? Let's sub in the things we know, and then I'll deal with it then. So let's start subbing them in. I know there's one missing. If you're really paying attention, like there's one missing. It'll be okay. It'll be okay. Let me just start subbing in. Sub in. So I get 2. What's the x at the particular moment we want to talk about? 1.6. Off to a good start. dx dt. That's how fast is the car moving. They didn't give me that. Why am I not stressed by the fact they didn't give me that? I don't care. Of course they didn't give me it. That's what I'm trying to find. What is the speed of the car? So the fact that this is dx dt in there, I'm not worried about at all. Then 2, y. Do I have the y value? Yes. He's 1.2 kilometers north of the intersection. Dy dt. That would be the speed of the cruiser.
So 120 kilometers per hour.
Yeah. Mm-hmm. It's definitely 120 kilometers per hour.
So,
Negative. Oh no. How am I supposed to know it's negative? It's making y get smaller. It's not a perfect explanation, but it'll do for now. D. How far apart are they right now? They didn't give me that. Okay. I'll freak out about that in a minute. They did give me dd dt because they told me that was 40. So life's pretty good. The solving here is going to be not too bad, except for I don't know what d is right now. How am I going to get what d is right now? Yeah, the Pythagorean Theorem, x squared plus y squared equals d squared. I sort of mentioned this yesterday. Sometimes it's like, what's going on? Meanwhile, you have this relationship. You're like, oh, I know x, and I know y, but how am I supposed to get d? And this formula is at the top of the question going, yo, don't leave me out of this. You know, like, come on. I can do some stuff here. So I go d squared equals square root of 1.2 squared plus 1.6 squared. And I get d equals, can I do this in my head? 144, 256, it's 4. Is it 2? Is it that easy? Someone on their calculator there? Yeah, it is 2. It was a 3, 4, 5 triangle multiplied by pi. Okay, it doesn't matter. 2. I hope you realize we're home here. I'll do the last few steps a little quicker here. 3.2 dx dt plus, no, it'll be minus 1. 2 times 1.2 times 120, negative 288 equals 160. Let me just check that. I don't want to make any mistakes here this late in the question. While my pizza's cooling. So then I get 3.2 dx dt equals 160 plus that 288, 448. So dx dt equals 448 divided by the 3.2, and I get 140 kilometers per hour. Moving! 140! We can find out how fast something's moving just by knowing how far from the intersection we are, how far they are, and a little radar that tells us how fast they're moving away from us. That is how much this distance is changing. Yeah? Max?
160 plus 288 is 388.
I don't think it is. The reason I felt good is because my answer matched up with the video. Yeah, I'm constantly checking it. My old video with no audio. This video, it's got audio, yeah. Hopefully it's working. Other questions? What a beaut. What a beaut. Is that a test hint? Maybe. I'll be looking for this one. I'll be like, can I get this one on there? Was it on the sample test? Can I use it? Yeah. It's a good one. It's a good one. Don't speed, please. Get pulled over tonight. Say, I was just seeing if Mr. Tao was right. I thought I'd drive 140 and see if you could catch me. Yeah. Oh, let's do another one, shall we? Okay, this is the tough one. This one's really tough. Really tough. And really interesting, though. A spotlight on the ground shines on a wall 10 meters away. A man, 2 meters tall, walks from the spotlight towards the wall at a speed of 1.2 meters per second. How fast is the shadow on the wall decreasing when he's 3 meters from the wall? What? I never read word problems like that. Never in my life do I read a word problem like that. Yeah? This is why people get upset about word problems. You read all that and you're like, how am I supposed to know anything? Don't read like that. A spotlight on the ground. Okay, spotlight on the ground. Just a second. Spotlight on the ground. I got it. All right, here we go. Yellow for spotlight, yeah. I don't know if you can see that. I'll put a little. There, now you can see it. Spotlight. Yeah? A spotlight on the ground shines on a wall 10 meters away. Okay, so a wall 10 meters away. Here we go. No. What color's the ground? The ground's got to be green, right? Like grass. Big diagrams. When you're confused about something, draw a big diagram so you can label what the heck is going on. A spotlight on the ground shines on a wall. Okay, the wall's going to be red. Like as if it's a brick wall. There it is, brick wall. And that distance all the way across is 10 meters. A spotlight on the ground shines on a wall 10 meters away. Good. Got the wall, got the 10 meters. Good. A man 2 meters tall walks from the spotlight towards the wall. Here's the man. See, I put his face on so you can see which way he's going. Towards the wall at a speed of 1.2 meters per second. How fast is the shadow on the wall? Oh, shadow. I need a shadow on the wall. Okay, so I'm going to go with orange for the spotlight beam of light for the top of his head here. And I'm going to shadow. So now color in with a thicker pen. And I'll go with like a brown here. Shadow. See how much better that feels? Instead of reading the word problem straight up like that, just go, hold on, get a picture here, and then I'll have a chance. A spotlight on the ground shines on a wall 10 meters away. Got it. A man 2 meters tall. Ooh, 2 meters. Hang on. Two meters. Good. Walks from the spotlight towards the wall at a speed of 1.2 meters per second. Good. I got how fast he's moving. Good. How fast is the shadow on the wall decreasing? Is it clear that the shadow will decrease as he moves along there? When you're really close to something, your shadow is giant. And then as you get closer and closer, or sorry, you get farther from the light source, your shadow will get pretty close. Think about it. When you get to the wall, your shadow will be exactly your height.
Right.
Yeah? All right.
So it's just how fast it's increasing when it's 3 meters.
Yeah. Yeah. What's the relationship here between the height of the shadow and how far he is from the wall? Huh? Let me help. If you've never seen one of these like before, they're really, really hard. I'm going to put, I just chose to put the X here. I'm going to make the X how far he is from the spotlight. You might have made a different choice. You might have put the X over here, and you'll still be able to do the question, but I'm going to put the X right there. And now, oh, it's good. It's so good. It's already done. As soon as I put that X on there, it's good. I'm going to teach a whole chapter of similar triangles from grade 10 in one example. If I went in this triangle here, and that angle was, say, 20 degrees. I don't even know what the angle is, but whatever it is. The opposite over adjacent in that triangle will be tan of 20. But this triangle has the same angle in it. So the opposite over adjacent of that angle will be the same. This is what similar triangles are all about. If you've got two triangles that have the same angle in them, then their ratios are all the same. Opposite over adjacent will be the same as opposite over adjacent. And what I get from that is that, I need an H for height of the shadow. Here's my very simple, incredibly complicated relationship between these two triangles. The height of the shadow divided by the distance from the light, h over 10, is the same as the height of the man divided by how far he is from the light source. Those two triangles are similar, so those ratios are the same. H over 10 is 2 over x. Again, if that's confusing, just think about it from a trigonometry standpoint. Trigonometry would say opposite over adjacent in this triangle has to be the same as opposite over adjacent in this triangle because they have the same angle. They're dealing with the same angle, and they're both right angle triangles, assuming that the wall is straight up and that the man is straight up. this results in an unbelievably easy relationship between these two quantities. H times x is 20. All I did was cross multiply there to get all the fraction stuff out of there. I think that's the easiest equation to deal with to find the derivatives with respect to time. I do have a little product rule looming here. Go to the left side, dh dt times x plus dx dt times h. Derivative of the first times the second plus derivative of the second times the first. And the derivative of 20?
0.
Still 0. We want how fast is his shadow decreasing. Which one is the shadow?
So
H. H is the shadow. I want dh dt. So I'm going to isolate this time. dh by dt will be negative h dx dt all over x. Did I isolate that right? Negative h dx dt divided by x. Yes, I like that. And then the big moment. Do I have this information? Do I have the height of the man? No, sorry. Do I have the height of the shadow at this particular moment? No, I don't. That's a problem. Do I have dx dt? How fast he's moving? Yes, I do have that. That's dx dt. I have dx dt. Do I have x? How far he is from the spotlight?
Yep.
How do I have that?
You know his distance to the wall, so you can just subtract that from the total.
Oh, yeah. He's 3 meters from the wall. So that means
7.
x equals 7. Sub in x equals 7. Dx by dt equals 1.2. But I don't know the height of the shadow.
Could we isolate everything but A? Could we isolate H and then solve for H to get our height or not?
The answer to your question is yes, but I don't know which equation you're talking about. Related rates are like this. You get right to the end, you're like, I'm missing something.
Well, the one where it equals 0, you have H multiplied by something, so you could just...
Yeah, but I won't know in that one. I won't know dh dt. That's what I'm trying to find.
Right.
Trevor?
Maybe you plug in x to the first one?
Yeah.
Watch out for related rate questions, because the thing you don't know, your original equation is like, yo, man, can I play or what? Am I in this? Am I, are you using me or what? You're like, hx equals 20. When x equals 7, h equals 20 over 7. I just sub 7 into that equation. Now I can do it. Okay, dh dt would be negative 20 over 7 times 1.2 all over 7. Let's see, negative 20, I didn't type that in right. Negative 20 divided by 7 times 1.2 divided by 7. Does it come out to something nice? No, it doesn't know yet. Negative 24 over 49 meters per second. That one is tough. I won't lie. There's a lot going on there. The math, you know, it's like the opposite of the tough derivatives lesson. The tough derivatives lesson, like, we know what we have to do, but 46 lines later, I don't know if I got it right. Here, it's like, I'm not even sure what I have to do, but the actual math, like subbing in 7, is not particularly difficult here. That's what makes this chapter hard. There's tough algebraic questions, and then there's tough conceptual questions. John, question? 7? Oh, yeah. So they told me how fast is shadow decreasing when he is 3 meters from the wall. If he's 3 meters from the wall, he must be 7 meters from the spotlight. And I happen to put x there, so x happened to be 7. Someone else might do this question and go, oh, I'm going to make this x, and I'm going to make this 10 minus x. And you'll get all you'll sub in differently, but you'll get all the same answers. You know, but I find the x in the smallest triangle. Years of experience tells me x in the smallest triangle often works out to be the best choice algebraically. But that's not always true. Any questions about that crazy one? Is there one more? I got great news. The last one takes me very little time. It's the hardest / easiest question of the bunch. But do you have more questions here? That one might take a little studying. Yeah, that's not one that you just look at and go, okay, I got that. You know, the police cruiser one, once you see it once, it's like, okay, I got that. But these ones are a little more tricky.
You can explain how you got the initial formula, like the dh dt x plus dx.
I took this h over hx equals 20 formula, and I went d by dt of both sides. So that's where I got the 0 over here. And then when I went to do product rule here, I went derivative the first times the second plus derivative the second times the first. And again, if you're a little bit behind in homework, the good news is the way we've planned this out is if you're a little bit behind in the homework, yeah, we've got 2.5 weeks here now to get ourselves back caught up. So if you've let yourself fall a little behind, you know what? And Christmas homework is the perfect thing. You know, like parents love to give you chores over Christmas, and this is the perfect way to get out of it. You know? Yeah. Say, hey, can you help me with these dishes? AP Calculus. You know how it is, Ma. I gotta go to my room and do 400 related rates problems. You know, like. Yeah. A different type of problem. Look at the hint. You see the hint on the left side there?
Oh, chain.
It's a chain. All right. Water flows into a bathtub at a rate of 20 liters per minute. This is a little more realistic. The constant rate of the water. Water comes in at a constant rate, usually. And the level rises 0.1 centimeters for each liter added. Every time a liter goes into the tub, we get 0.1 centimeters. Find the rate of change of the height of the water with respect to time. Your brain freaks out. You're like, they didn't tell me the shape of the tub. I don't have a formula for volume of random tubs. You know, they didn't tell me the tub's a hemisphere. They didn't tell me the tub's an oval. They didn't tell me anything. So my job, I got to write something on the right-hand side of this line that makes you go, oh yeah, because this is actually a low number of steps question. What I'm going to do instead is do this question a completely different way, not how we'd want to do it in calculus, just so you can see what's going on. We know that the volume is increasing by 20 liters per minute. I'm just going to write that down. And beside that, just in my brain, my brain's just going, okay, 20 liters per minute, and then over here, 0.1 centimeters per liter. Okay, now strap in here, because my job here is to say something that makes you go, oh, duh. And then start rethinking how you've thought about units the whole time. 20 liters per minute, 0.1 centimeters per liter, and I want the change of height with respect to time. I want you to listen to what's happened there. We went from no hands to a few hands, and then a couple of noises.
So 1 centimeter per liter is like our change in height, and 20 liters per minute is like our change in time.
Yeah. This is good thinking. Heather, what were you going to say about it?
This is 0.1 centimeter for every liter added and 20 liters added every minute, which is multiplied per liter by 0.1 centimeters.
She's phrased it beautifully, right? Since it's 0.1 centimeter for every liter, and I'm getting 20 liters every minute, it must be just these two things multiplied together. And units are like that. Take a look at the units.
Sorry for the interruption. All teachers that have not sent down their lists and tests, could you please do so now? Thank you.
What's that?
Did she get a COVID test too?
That was a list from yesterday? Is that what she's talking about? Or
Her voice sounded.
Oh, that's why she did the announcement. She needs a COVID test. I get it. All right. Take a look. If I were to multiply these two things together, what would I get? Not the numbers. I get the numbers. Today's unit day. On the top, I get liters times centimeters. On the bottom, I have liters times minutes. The liters would cancel, and it'd be centimeters per minute. Heather sort of said it in a logical way. Let's just use my brain here. But the units can also guide you there and show you what's going on here. That's leading me to believe it's multiply. But check this out. This is good. I want change of height with respect to time. I want dH dt. They've given me dV dt, change in volume with respect to time. And they've given me dH dV.
Perfect.
Oh, perfect. Yeah? Chain row's like, the whole time we were over here, chain row's sitting here over going, what are you doing? Yeah? Well, stop that. Just write down the chain rule. It tells you what to do. You want dH dt? You first got to go, how much is the height changing with respect to volume? 0.1. How much is the volume changing with time? 20. Answer 2. I just multiply them together. What's the units? Can you see the units on the page?
So centimeters per minute.
Centimeters per minute. It's right there. Yeah? Great stuff. Great stuff. Powerhouse stuff. And really starting to move towards, where's the application here? Sewage running into the river. Is it going to be too polluted for the animals, or is it not going to be too polluted for the animals? We're right on top of those type of questions now. Climate change is laying right here. You know what I mean? Some serious math is laying right here. You have any questions about that one? That one's tough. I won't lie. That's tough.